Hi, I am Lakshay Kumar from SPCE, final year student, where I am currently pursuing computer science course, Bachelor's of Engineering. And our final year project is multimodal AI-driven precision agricultural system for smart farming. And I am myself, and my teammates are Srivas Bharatwaj and Surya Narayan. And our domain is basically of AI and ML, which is like artificial intelligence and machine learning basically. And then what are the contents which I'm going to present now are nothing but problem statement, abstract, and then literature review, issues and challenges, proposed work, system architecture designs, and system requirements, and tool modules and description, and implementation screenshot, and experimental results, and the novel contribution and references. These are the things which this PPT contains, where each component contains each things which are, you know, basically explain what we have done in the project. So let's not waste time and let's move to the next section. In the present agricultural ecosystem, effective crop health monitoring continues to remain a significant challenge, particularly for small marginal farming communities. Traditional crop surveillance practices rely heavily on manual field inspection, expert consultations, and costly sensing infrastructure, making them economically unviable for large sections of rural farming. Furthermore, existing digital agricultural solutions exhibit a strong dependency on continuous internal connectivity and centralized cloud services, which limits their application. And remote regions with unstable network infrastructure, the delayed identification of crop diseases and vegetation stress conditions often results in irreversible yield loss and financial instability. Hence, there is a pressing requirement for a scalable, cost-effective, and intelligent crop monitoring system capable of operating with minimal external dependency while delivering actionable, actionable, actionable insights to farmers, basically. And this is the problem statement which we have taken in order to solve this. And coming to the abstract phase, this project proposes an AI-powered precision agriculture model application for intelligent crop health monitoring tailored to small and marginal farmers. Conventional crop surveillance approaches are often cost intensive, infrastructure dependent, and lack explainability in decision making. To address these challenges, the proposed system employs a transfer learning creative deep learning architecture, such as MobileNet V3, large which is confirmed and trained for robust leaf disease classification, enabling accuracy and reduced computational overhead suitable for mobile deployment. The train model is implemented in PyTorch with ONNX export for cross-platform deployment and ensuring operational continuity in low connectivity rural environments. To enhance model transparency, GradCam is integrated to provide visual explanations by highlighting affected regions in the leaf image, thereby improving user trust and interpretability. In addition to disease detection, vegetation health metrics including NDVI, EVI, and SAVI are computed from Landsat 8 imagery via Google Earth Engine API. An XGBoost tensor fusion model with a confidence adaptive fusion algorithm integrates disease probability, vegetation index, and weather stress index to generate a comprehensive crop health score. By integrating explainable AI, remote sensing analytics, and mobile-based deployment into a unified framework, the system supports data-driven decision making and promotes scalable, cost-effective smart farming practices. And Coming to our issues and challenges, delayed identification of pathological systems resulting in irreversible yield degradation and economic technical barriers. And moreover, what it is like is economical technical barrier and associated with continuous to field monitoring solutions, limited interpretability of satellite-derived vegetation metrics for non-technical users, excessive reliance on cloud infrastructure and the persistent internet availability and the absence of a consolidated mobile platform addressing using agricultural analytics are some of the problems which we're going to solve. And then coming to proposed work, design what we have done is designing a for Flutter-based application enabling user authentication, GPS-based field map, and real-life image acquisition for crop monitoring. Implement a transfer learning-based deep learning architecture using MobileNet v3 and fine-tuned on a plant village dataset and implementing in PyTorch exported to ONNX for deployment for efficient on-device classification. Integrate DATCAM to provide visual interpretability by highlighting infected regions in the leaf image, enhancing the transparency and user trust. Retrieve Landsat 18 satellite imagery to compute vegetation indices, NDVI, EVA, and SAVA via Google Earth Engine API for field crop health assessment and stress reduction. Develop an XGBoost Ensemble Fusion model, 91.7% CV accuracy with novel confidence adaptive fusion algorithm that dynamically mm, adjust using modality weights based on a reliability scores, achieving 92.20 test accuracy across 38 species classes and storing results in a Node.js backend and presenting them through an interactive dashboard with weather insights are the things which we are going to do. Also, in here, if you want to see a diagram, detailed architectural diagram, first is input sources will be leaf image. From leaf image, it will go to the disease detection, disease probability, and GradCam explainability, as I have explained before. From there, the satellite data will be used for NDVA, UVA, SAVA, normalized vegetation index portion. Weather data, temperature, deviation, humidity, deficit index, weather stress index are going to be we're going to use. And then what we're going to use is disease probability will be calculated, and the vegetation score will also be got as an input. And stress index will be used, and then multi-model fusion like XGBoost model inputs like disease probability and vegetation index, weather stress, which will be included, where XGBoost will be used to calculate the CAF score. The CAF score is a normalized thing where it will be used to predict the crop health score, high risk or moderate or healthy, and somewhere around that. Then we come to the hardware requirements of this project. Processor is a normal computer processor. An average PC processor is enough to do this. Intel Core i5 or higher or Apple M1. And then RAM is 8 GB is minimum recommended. 8 GB minimum and 16 GB is recommended. And storage is 256 GB SSD, mobile device, Android and plus 4 GB RAM. And then GPU is NVIDIA GeForce RTX 5050, a laptop GPU used for training 6 GB used for training where 6 GB VRAM is recommended. And the software requirements is operating system there it can be anything. Mobile framework will be Flutter SDK and backend runtime will be Node.js and database is Postgres and IDE will be VS Code. ML framework will be PyTorch plus CUDA plus ONNX where version controls will be GitHub and Git and API testing will be Postman. Then technologies used will be for front-end Google Maps SDK, camera plugin provider, Flutter. In machine learning and AI will use like PyTorch MobileNet V3 Large, ONNX Export, and OpenCV, GradCam, and XBG. A remote sensing and visitation analyzer uses Sentinel to satellite imagery, NDVA, EVA, and SAVA. Computation via Google Earth Engine, and backend will be Node.js, Express.js, Postgres, and Multer and Weather API. And coming to this, Flutter modules and its description will be Flutter and mobile application, user authentication, GPS-based field mapping, and real-time leaf image acquisition via camera plugin and provider statement. Disease classification will be of MobileNet V3 plus ONNX. Explainability via platform there it can be used to find the infected parts of the leaf. Vegetation index will be remote sensing, NDVA, EVA, SAVA, where we are using Landsat imagery via Google Earth Engine API. XGBoost, TF Fusion, and plus backend is used for TF Fusion is used for plant health prediction system, where Node.js is used for making connection with Postgres and saving the data and retrieving whenever it is requested. Coming to implementation screenshots, it is nothing but where disease detected is high and confidence will be high for an early blight, and then where our training loss was around that around say somewhere around we have given an epoch of around 5 5 where we have just trained it separately. I mean in a series manner, and then instead of training it at a single time. And then when it comes to recommendations, recommended actions, it also gives the preventive measures in order to overcome the disease. Here, score and everything is visible. And coming to the implement screenshot, where GradCam is used to find the infected areas, as you can see in this video. So, and then coming to CNN only, and this is for comparison model where CNN is fixed and one with other comparison. And coming to our front end, this is our front end, and this will be our this is our application basically. This is our front end, and where it gives all the disease scores and metrics and insights and how does it calculates and everything. And experimental results are nothing but test accuracy 92% and precision is 92 recall and effort for everything is 92% and AUC is 0.922 and the model is MobileNet V3 large and then classes are 38 disease classes and training images are 62,000 to 63,000 to 65 and value is 7,030 and the test accuracy test images are 17,572 and GPU is NVIDIA RTX 5050 laptop. And coming to phase one, it was like 98% and phase two 99%. Final test, it gave us an accuracy of 92%. And now the problem is fixed weights cannot adapt across different crops, climates, or seasons. One size fits all, even when a modality is unreliable. CA solution per sample reliability scores computed at inferences CNN is equal to 1 and then normalized channel entropy and NDVA is linear scale from B to N. And weather is nothing but a weather as used for calculating the future predictions and the live result will be around CNN and all the metrics will be given as you can see in this video. In this video. So, and references are we have taken around 5 references where they have published which projects and papers which are related to our project. And we have taken them as references as Sharma, A. Kumar, and P. Singh for mobile, Flutter mobile application for real-time plant disease detection using transfer learning. And then TinyML for plant disease detection, deploying deep learning models on microcontrollers. And then NDVA trend forecasting using time series analysis for precision agriculture. And four will be edge boosting crop disease detection framework with hybrid cloud edge architecture. And Leaf Science, a low-cost diagnostic device for plant disease detection using multispectral imaging. And there, these are the other reference papers which we have also taken online, where it has around overview of radiometric and biophysical performance of modest vegetation indices and monitoring vegetation systems in Great Plains with ERTF and soil adjusted vegetation index and searching for mobile net V3 and still GradCam visual explanation for deep networks via gradient-based localization. These are the references we have took around 20 references we have taken, and then around 25 references is total. And then when it comes to the project, and this is how we have done it, and